Hello everyone. Let's just give 1 or 2 minutes in order to have your friends, and then we'll start in very short time. The second session, we are still in the free vibration, chapter 2. It will take, I think, 2 sessions in order to cover this chapter. Hello everyone. If you have any question from the previous session, you can ask. Otherwise, we will start the today's session, and this session will be recorded. Just let me know if you hear me very well. Okay. Okay, the first problem would be problem 2.52, and determine the effective stiffness of the system shown in the figure 2.52 in terms of displacement at point X. So if I want to plot the sphere, there is a spring with a stiffness K, and there is a mass M, which is attached to the rigid links, and this is going to pass through point O. And at the end of this link, there is a spring, the stiffness K2, and the displacement from the upper mass is given as X, okay? This is the direction of the movement of the mass, and this is point O. And this is, okay, we are supposed to find effective stiffness as a function of displacement X, okay? So as I told you in the previous session, in the system that several rigid links, such as here, which are linked, we could use effective stiffness and effective mass in order to make this the model, the system very simpler. Okay, we could show this complex system as a very simple effective mass and effective stiffness. Analysis of vibration for us for this system is much simpler if we use this effective mass and effective stiffness. We could easily derive equation of motion plus K effective multiplied by X is equal to 0, free vibration, right? So here we want to find effective stiffness. So for effective stiffness, you have to write all the potential energy, right? And for effective mass, you have to write and make summation of all kinetic energy. So let's start. So before a start, you have to always relate all the rotational movement into a linear displacement, or you can transfer and change all the linear motion into a rotational motion. The point here is that you have to have at the end all the terms in terms of theta or all the terms in terms of x. Since we are asked to derive effective stiffness in terms of x, we try to relate any rotational movement of any link into a linear displacement. So here, what we can do, we could draw this line, and if I call it this angle theta, this would be also theta, right? So I can say this is x, this displacement, I can call it x, and I can call this displacement as x2, right? So this length is given as b, or you could assume this is given as b, and this length is given as a, right? A. Okay. So x2, O, A, and B, right? Theta and theta. So you could write so if I write sine of theta, right? Sine of theta in the upper triangle, you could write x over a, right? Therefore, x over a. It's very difficult to write. A. So therefore, x is a sine theta. So for deriving, always keep in mind, for deriving equation of motion, our focus is just we apply very small movement, okay? So for deriving equation of motion, we try to give a very small movement, right? A small movement. Therefore, this is a good assumption. Theta is very small. Theta is very small. Therefore, theta is approximately equal sine of theta. Therefore, in all of our calculation, we could easily say that x is approximately equal to a multiplied by theta, right? So here, by just taking a look at this triangle, you could easily say, you are not supposed to prove in the exam. I was trying to give you why this is, why x can be equal to a multiplied by theta, and why x2 can be related to rotational movement, right? B multiplied by theta. In a similar manner, x2 is equal to b multiplied by theta. So by using this trigonomic and mathematical relation, we could easily relate any rotational movement into a translational movement. So try to take a look at to the figure. I'm gonna write at first all the kinetic energy. Suppose we are asked to find effective mass as well, right? Effective mass. Suppose, so all the kinetic energy, the upper mass, 1/2 m x dot square is the all kinetic energy related to the upper mass plus the kinetic energy of the rigid links, 1/2 I mass moment of inertia around point of rotation O theta dot squared, and total potential energy is equal to the potential energy is the energy that is stored in the spring. In the upper mass, we have a stiffness. We have a spring with a stiffness K. Therefore, the potential energy would be 1/2 K 1x squared plus the lower spring has the potential energy of 1/2 K2 x2 squared. So anybody can tell me what are the other options for potential energy in other, for example, problem? What kind of other term we could have for potential energy? If you have this system, right, the mass, the pendulum, for you have to use mgh. You have to calculate mg delta h if you want to derive effective stiffness, right? So, okay. So once you write this term, at the end you will write 1/2 K effective mass x dot squared at any point you want equal to 1/2 effective mass moment of inertia or effective mass theta dot squared at a specific point, right? So and here which is equal to 1/2 K effective or equivalent x squared or 1/2 torsional spring theta squared, right? Depends on the problem. So since we are asked to calculate the effective stiffness and effective mass at point x, we therefore change any theta into linear motion. So x is equal to b multiplied by theta. You could easily take derivative. X dot would be b theta dot. Therefore, theta dot can be replaced by x dot over b. That's it. So you have to plug in this relation into the above relation. Therefore, T would be, the total kinetic energy would be 1/2 m x dot squared plus 1/2 mass moment of inertia around point O x dot over b squared, which is equal to 1/2 m plus I over b squared multiplied by x dot squared. In the previous semester, I noticed that all the students just gave up as soon as they reached to this point, and they said this is in the assignment. This is the final answer. This is not the final answer, my friend. You have to write this is equal to 1/2 k m effective x dot squared. Therefore, effective mass is m plus I over b squared. This is the final answer. You have to reach to this point. This is a complete answer, right? This is not effective stiffness, this equation. So this is the effective stiffness, mass, and similarly we could write effective stiffness. The total kinetic energy would be 1/2 k1 x squared. The first term is already expressed in terms of linear motion x, the point that we are interested to derive the potential formula, right? And the second term, however, is based on the second term was expressed in terms of x2, right? K2 x2. You have to, in a way, change x2 into x. Why? Because we are asked to find effective stiffness at x. So anybody knows how can I relate x2 into x?
With theta, you do x1 over a.
Exactly. Thank you for your response. We obtained that a x was b over theta, and also we had x2 a theta, right? So
Plus the inverse.
exactly. Okay, x2 from the first equation, theta is x over b, right? So you could plug in theta here. Therefore, x2 is a multiplied by theta. Theta is x over b. Therefore, x2 can be written as a over b multiplied by x. So if I plug in back, I'll have...
Sir, I think you have a small mistake.
Okay, I will go
with x equal to b, it's x equal to a theta, no? And x2 equal to b theta.
Okay, I will take a look at. Thank you for mentioning that. Okay. If we go through the... So here, if we... x is...
Oh yeah, I just saw my mistake. Sorry about that.
Okay, no problem. X is b theta and x2 is a theta. So we are here. Okay. Okay. So therefore the potential energy, the total potential energy would be finally 1/2 k1 x squared plus 1/2 k2 a over b x squared, which is equal to 1/2 k1 plus a 2 b2 multiplied by k2 x squared, which is equal to, you have to write equal to 1/2 k effective x squared. Please do not give up here. You have to continue, my friend. You have to continue and write. Therefore, k effective is equal to K1 plus A squared B squared K2. These are the final answer, and you could at the end derive the equation of motion of the system M effective X double plus K effective X is equal to 0, and then at the end you could design any system, any rigid links based on the response of the system. You could increase the stiffness, you could decrease the mass, so it depends on the problem. So if you have any question, just ask me, otherwise we will go for next problem. Are we good so far? So this is how you have to derive equation effective mass and effective stiffness. So the next problem would be .20. So there is a system, this is bar, there is a tire, this length is 50 inch, and this length is 24 inches, and the weight of its total assembly is 38 pounds. So a steel shaft 15 inch in length and 1.5 inch in diameter. So diameter is also given to us, the 1.5 inches is used as a torsion spring for the wheels of a light automobile, as shown here. Determine the natural frequency of the system. So we are supposed to determine the natural frequency of the system if the weight of wheel and tire assembly, wheel and tire together, okay? The weight of wheel and tire assembly is 38 pounds, and its radius of gyration is given as 9 inch around its axle. Discuss the difference in natural frequency with the wheel lock and unlock to the arm. So we are supposed to find natural frequency in two cases. First case, wheel and tire assembly is locked to the arm. In a second case, we have to find the natural frequency of the system when wheel and tire assembly is unlocked from the arm. It's free from the arm. This is arm, right? This is arm. So the natural frequency of this torsional system, you could easily write the omega n is K over M for linear system. For torsional system is like here, it is equal to torsional stiffness over the mass moment of inertia, around point of rotation O. O here, it means this point, this axle, this axis. O, okay? So let's call it, this is O prime, okay? So since we are facing a torsional system, we will use this omega m is equal to torsional spring over J over naught, J naught. So the torsional spring KT is equal to, so anybody knows what is the stiffness here? Which part is a stiffness? We have a tire and wheel assembly in the right. There's a rigid arm and we have a steel shaft. We could regard this steel shaft as a torsional spring, right? So therefore we have a simple system. There's a spring and mass, rotational mass. So KT then can be written as GI, polar moment of inertia, over GI over L, GI over L. This is the stiffness of a shaft. Okay, this is the L. G is shear modulus. You could find shear modulus of the steel from the table. I think it's made of steel, right? Steel shaft. You could find from the table, but you have to be very careful regarding the units. The units is very important. Here we are dealing with UK system, rather ISI, right? We are dealing with UK in this system. So in order to find the natural frequency, let's calculate the numerator, KT, and then we will go for denominator as a second step. Once you find numerator, KT, and denominator, J naught, you could easily find the natural frequency of the system. Let's just focus on the numerator, which is KT. KT is GI over L, and I is polar moment of inertia. Polar moment of inertia for the shaft, area moment of inertia, or area moment of inertia. So second polar moment of area, second polar moment of area. So IP is equal to pi d to the 4 over 32. So we have d, you have to only plug in d as 1.5 inch. D is 1.5 inch, right? 1.5 to the power of 4, 32, therefore IP is 0.947 inch squared. So once you obtain I, you could easily find K. If you go through the table, you will find G as, in the SI system, G is based on the Newton per meter square or Pascal in a metric system, SI unit. However, in a UK system, is based on pound over inch squared. So here is G, shear modulus of the shaft is 11.2 multiply 10 to the power 6 pound inch squared, right? For each radian, you need to apply this pressure, right? For each radian, for rotating each radian, you need to apply this force for any inch square of the shaft. So therefore, KT is GIP over L. G is 11.2 multiplied 10 to the power 6 multiplied by calculated IP as 0.497 over L. L was 50 inch, right? Therefore, which is equal to 0.1113 multiplied 10 to the power 6, and the unit is pound inch over radian. So we calculated the numerator, and then once we calculate the denominator, we could easily find the natural frequency of the system. So KT is done. So JO, the moment of inertia of the system around point of rotation, right? So JO. So let's focus the first case when the first case is the case when the wheel lock to the arm. Locked to the arm. I need your attention here, please take a look at here. So there is a shaft and there is an arm and there is a wheel assembly. So once the wheel and tire is locked, if I draw a line here during the rotation of the system, at any time, so as soon as you rotate the once you rotate the tire and wheel assembly, you have to consider the inertia of the wheel apart from inertia that the whole wheel has around point O. So if I call it O and here O prime, and let's call this length is D. For the locked case, the total inertia, total resistance, the system that has for rotation, okay? The total resistance of the total resistance of the system in response to any motion, the total mass moment of inertia around point O is J around point O prime plus MD squared O prime. J around O prime plus MD squared. The second term is related to the theorem of parallel axis, right? So you have to understand that since the total assembly wheels and tire is locked to the arm, you have to calculate the inertia. If you take a look at here, you will see that the red line in the wheel assembly is also rotates. So we have to use some energy to rotate the wheel also, right? So apart from the arm. So since the red line is rotating, you have to consider the rotation, the mass moment of rotation of the wheel around point of O prime, and in total around point O. So for calculating the J around point O prime, if we were facing a very simple disk, for example, if we were facing very simple and unique, which mass is evenly distributed around this system, we will have a specific formula. For any arbitrary mass, for any arbitrary system, if you want to calculate the mass moment of inertia around any arbitrary axle, like O-zegon or O prime, we could take advantage of the radius of gyration. We could simplify the system. We could simplify a system. We could imagine that all the mass of this complex system can be concentrated at a specific distance, so-called radius of gyration, RG, radius of gyration. So in the laboratory, by rotating the system and measuring acceleration, velocity, displacement, you could calculate the radius of gyration. Here, fortunately, you are given the radius of gyration of this complex system, tire, ring, and all the assembly, including wheels and tire, right? So once you have radius of gyration, you could therefore find the radius, the mass moment of inertia around point O prime, right, is equal to mRg squared. mgr squared. So therefore, for the first case, the total mass moment of inertia around axis O is JO prime plus md squared mRg squared plus md squared. Rg is given 9, m9 squared plus md is 24. 24 is given 24 inch squared. In total, the J for first case is equal to 657 multiplied by mass of the system, and the unit is pound inch squared. So we are done for the first case. And at the end, we will calculate the corresponding natural frequency. Let's go over the second case that the tire and wheel assembly is not locked to the arm. And if I draw it here, for second case, if I draw this red line, and if I rotate the system, since wheel and arm is not locked, you will see that the red line will not change at any point of rotation. At any time, so you don't have to consume any energy to rotate the system. It is free. It is free of rotation, and you have to just consider it as so. Yeah, at this time also, as if we are dealing with a pendulum, right? For pendulum, J around point O is ml square, right? So here, therefore, J naught is equal to J O prime plus md squared. There is no any resistance, my friend. That's why we don't have any mass moment of inertia around point of O prime, right? O prime. So like a pendulum, you have to just write md squared, ml squared. So if you have any question, you can ask. So this is how we calculate JO for an unlocked case as md squared m24 squared equal as 576 mass pound inch squared. So we obtained the J naught, and we had previously calculated the natural the torsional stiffness. Therefore, omega n can be calculated as KT over J naught 1 KT J sub O2. So KT was calculated as 0.1113 multiplied by 10 to the power 6 over M 657, and for the second case is equal to 0.113 10 to the power 6 over 576 multiplied by M. And M is nothing but mass, is nothing but weight over G. Before plugging energy, you have to check the units, right? So omega n1 would be 113 10 to the power 6 over, in the inch system, G is 38.6 inch over second squared. If we were dealing with SI, G was 9.8 meter squared, and for a foot, G was 32.2 foot second squared here. Therefore, if you plug in G as, so 657 multiplied by mass. Mass is W over G. G will go in the numerator, 368. The natural frequency for the first case would be equal to 41.48 radian per second, which is equal to 6.60 hertz or cycle per second. For the second case, similarly, you could find the natural frequency as K torsional spring over J unlocked. (570) multiplied by mm is nothing but weight over G will go in the numerator. Omega n for case 2 would be 44.30 radian per second, which is equal to 7.5 hertz. This is how we obtain the natural frequency in two cases. As you see, omega n is K over J. By increasing the J, the omega n will be decreased, right? So if you want to decrease the natural frequency, you could either decrease directly the stiffness or increase the J. So this is how we obtain the natural frequency for two cases. If you have any question, just ask me. No question? Are we good so far? So how many? Just 3. Okay. So the next problem would be 2.30. Very simple problem. Very simple. So 2.30 is just so there's a stiffness K1 X M1. There's a disk attached to this mass with radius of R2 and mass moment of inertia J2, which is connected to another disk which has a radius of R3. This disk attached to a shaft, which is torsional shaft, which is attached to the wall. The torsional stiffness is K3. So for the purposes of analysis, it is desired to reduce the system of this sphere to a simple linear spring mass system of effective mass M, effective and effective stiffness. So we are supposed to find, for the sake of simplicity, as I told you, we usually simplify any complex problem to a very simple mass spring system. Effective mass and effective stiffness. So we have to find effective mass and effective stiffness of this system. So since it is written, it is said that try to find effective mass and effective stiffness based on a linear motion, you have to change any rotational movement into a linear motion, which is given as x here. So you could say that this is so what happened? Okay, this is a theta 2, let's call it theta 2, and let's call this angle as theta 3. Okay, so we could relate x. So theta 2 r2 x2, therefore x. So x can be written as r2 multiplied by theta 2. This is one relation, and another relation we could write here, theta 2, theta 3. So r2, r3. This length is the same for once these two disks is rotating. Therefore, we could write r2 multiplied by theta 2 is equal to r3 multiplied by theta 3. So let's go for calculating effective mass. You have to calculate all the kinetic energy of the system. So all the kinetic energy of the system is, we have a linear motion for the mass m, 1/2 m, x dot squared is therefore the kinetic energy. For the first x, the kinetic energy is 1/2 j2 theta dot 2 squared, and for the third, this 1/2 j3 theta 3 dot squared. So we have to change theta dot 2 and theta dot 3. We have to write it in terms of x. So we obtain that x is r2 theta 2 and also r2 theta 2 is equal to r3 theta 3. Therefore, at the first case, theta 2 is x over r, and you could take derivative from both sides. Theta dot 2 is equal to x dot over r2. You could easily plug in the equation, and from this relation, theta 3 is nothing but r2 theta 2 over r3, and also r2 theta 2 is already obtained as x over, there is r2 in the numerator and denominator, we could cancel out from both sides. Therefore, therefore the So therefore theta 3 is x over r3, and you could easily take derivative. Therefore theta dot 3 is x dot over r sub 3, right? By plugging these two relation into the kinetic energy, and you could okay, therefore T would be 1/2 m1 x dot squared plus 1/2 j2 x dot over r2 squared plus 1/2 j3 x dot r1 2. You could factor out, therefore T would be 1/2 m1 plus j2 over r2 squared. Pardon? I couldn't hear your voice. Sorry? Who is talking? Just let me know. What is your question? Sorry, I didn't hear you.
Sorry, I think it's me. My microphone was open. Sorry.
Okay, no problem. So m1 plus j2 over r2 squared. So I think I made a mistake here. R3. Multiplied by x dot square, which is equal to 1/2 m effective. Therefore, m effective is equal to m1 plus j2 r2 squared plus j3 r3 squared. And similarly, we could write the total potential energy. There is a spring in the upper section, 1/2 k1 x squared. There is a torsional spring in the bottom plus 1/2 k torsional theta 3 squared, right? You have to relate in some way theta 3 in terms of x, which is obtained as x over r3, right? You could easily plug.
Sorry, I have a question.
Yes.
Is there a question between? Is there a difference between M effective and M equivalent?
No, there's no any. There's just matter of terminology. There's no difference, my friend. Thank you for the question.
Okay.
More or less the same. Equivalent, effective. It's the same. So we want to just simplify the system. That's the whole point. 1/2 x plus 1 kt or k3, let's call it k3, x over r3 squared, which is equal to 1/2. You can factor out 1/2 from the two terms, then you will have 1 plus k3 over r3 squared which which is equal to 1/2 K equivalent or K effective X squared then effective stiffness of the system is K1 plus K3 over R3 squared. So we are done with this question as well. If you have any other question, just ask me. So the next problem would be 2.40. 2.40, I'm going to solve it next session as we have not reached to the logarithmic decrement. So we will go for the next problem. And 2.42. So it's very important. This question is very important. In the midterm, maybe you will ask such problems. You have to derive equation of motion. So I need your full attention for this question. So let me just draw the system. There is a torsional system. The system is include a mass M, which is attached to a damper C, and at the end there is a spring stiffness attached to the ground, right? So spring with a stiffness K, damper with damping C, mass M. This length is A, and this length is B. And this point, let's call it O. Write the differential equation of motion for the system plotted here and determine the natural frequency of damp oscillation. So at first, we need to calculate we need to derive equation of motion, differential equation of motion, and part 2, we are supposed to determining damp natural frequency, omega d. And then we have to calculate the critical damping coefficient, critical damping C critical, right? So equation of motion is everything. Once you obtain equation of motion, the rest is very easy. So if you take a look at here, there is a pure rotational system. These links can rotate around point O, right? We could take advantage of Euler formula for a rotational system. Summation of momentum around any point is equal to J of the system around that point multiplied by theta double dot, rotational acceleration. So you have to, before using this Euler formula, you have to determine a positive direction. Which can be either clockwise or counterclockwise, positive direction. So here let's So 2.42, and let's find my notes. Okay, let's rotate the system. Let's consider the counterclockwise is positive direction, right? Positive direction. Once we determine the positive direction, the second step is disturbing, is oscillating and moving a system a little bit in order to find what kind of forces will oppose the motion. Since we consider the positive direction is counterclockwise, it is simpler and it is easier to just rotate the system in the direction of the assumed direction. So since the positive direction is counterclockwise, I deliberately displace and rotate system counterclockwise in order to just, for the sake of simplicity, in order to derive equation of motion in a simpler manner, in a simpler format. So if I rotate this link to this point, like theta, so this point will reach to this point. So let's call it x2, x1, and this point will go to this point x2, right? As soon as you rotate the link, this spring will oppose the motion. The spring force is kx2. Apart from a stiffness, apart from the spring, the damper will also oppose the motion. So there is a damping force as Cx.1. The damper is mainly dependent on the velocity of motion. However, a spring is always dependent on the deflection, right? So if you take a look at here, you have in the left you have a damping force, in the right you have a spring force. So in order to derive equation of motion, you could simply use the Euler formula, summation of momentum around point O, let's call it point O, is equal to J around point O theta double dot. So what are the summation of momentum? So this spring, this damping force multiplied by this arm will create a momentum, and the spring force multiplied by arm B will create a clockwise momentum, right? So both damping and spring will create clockwise momentum. So since the first momentum due to the spring force so the first momentum is due to a spring, is to the damper force, so force multiplied by related arm this is force, damping force, and this is arm, right? So since this create a clockwise momentum, you have to write negative sign here, and also the second momentum is due to the stiffness spring, which is stored a stiffness of kx2 multiplied by related arm, which create a momentum. So arm force, the result is momentum, right? Momentum due to the spring, since the multiplication of a spring and arm will create a clockwise momentum, you have to put negative. And here, which is equal to J run O theta double dot. J is nothing but M L squared. L is A, right? M A squared multiplied theta double dot, right? So you have to manipulate this relation and simplify. By simplifying this relation, we could reach to this point. We could reach to this point as, and also since we are dealing with a rotational system, it is better to change all the x and x prime in terms of theta, right? You could simply write here, if I assume this angle is theta, therefore x2 is nothing but b multiplied by theta for a small oscillation, and x1 is nothing but a multiplied by theta. Therefore, you could easily take derivative, right, from the both sides, and if needed, you could plug in x dot 1 as a multiplied by theta 1. So if you plug in x dot 1 and x2 as a function of theta, therefore you will have m you will have minus ca theta dot a minus k b theta multiplied by b. You will have m a squared theta double dot. By further simplification and manipulation of this equation of motion, ca theta dot you will reach to this equation theta double dot plus c over m theta dot plus k over m b over a squared theta equal to 0. So it is better, for the sake of simplicity, it is better to make the coefficient of theta double dot as 1. This coefficient as 1 for the sake of simplicity, and this then would be omega n squared if you put 1 as a coefficient of x double dot or theta double dot. So we are done with equation of motion. for the first part, and part B, we are supposed to find the natural frequency of damp oscillation. Omega d is nothing but 1 minus square root of 1 minus zeta squared damping ratio multiplied by omega n, right? So in order to calculate damp natural frequency omega d, we have to first calculate damping ratios. Zeta is C over C critical, and C is given in the problem, just assume as C, and C critical is 2m omega n, right? Omega n can be written as square root of k over m, right? And this m can be written as radical m multiplied by radical m, right? So pen. Okay, so therefore C over 2m m, right? Radical k over radical m, one of these will be cancelled out, therefore would be C over 2km, right? So C critical, or simply, or you could write C critical is 2m by taking a look at equation of motion. We could easily say, as I told you, this is omega n squared when this coefficient of theta double dot is 1. So we have here already obtained the omega n.
Sorry,
Yes.
is there a way that you can show the whole page and not like line by line? Because it's a bit hard to follow.
Okay, so yes, I will try to do that. So we basically, so I don't know how. So just I have to zoom out. I don't know how to. So here we just so how can I zoom out? So view. So I will take care of this in the next session. So thank you for letting me know.
No worries.
Pardon? Okay, so C critical is 2m omega n. We already obtained omega n as coefficient of x or theta. This is coefficient of x or theta when coefficient of x dot or theta dot is 1. So we already obtained the natural frequency. We could easily find the critical damping to m omega n as 2mb over a k over m. So zeta therefore can be obtained critical damping ratio as c over c critical c over 2b over a k m. Zeta is done, right? Once you obtain the zeta, damping ratio can be calculated as 1 minus zeta squared omega n. Omega n is obtained and zeta is obtained. Therefore, damped natural frequency can be easily found as omega n, which is already obtained, multiplied by 1 minus c zeta squared c squared over 2b over a k m squared. So we have to make it simplify. B squared a squared k over m minus b squared k over a squared m multiplied by a squared c squared 4b squared km. You have to cancel out this b squared and b squared and a squared by a squared, and therefore also k by k. You will have at the end omega d as p over m squared km minus c over 2m squared. So we are done with this equation. As I told you, the first part was deriving the equation of motion. Which we obtain here. Equation of motion here we obtain, and then we reach to this point. We make the coefficient of theta double dot 1, therefore the coefficient of theta is omega n, and omega d is omega n multiplied 1 minus zeta squared. The first part, equation of motion, damped natural frequency, and the last critical damping coefficient, C critical. We obtain all the parameter as this. So if you have any question, you can ask. Otherwise, we will go for next question.
Can you show the final answer again?
Okay. At first, we had a torsional system.
Oh, it's okay. I got it. It was just like for the final answer.
Okay, the final answer. Okay. So this is the omega d, right? This is the final answer for omega d, and equation of motion is c over m theta dot plus k over m e over a squared theta is equal to 0, and this is the final equation of motion. Equation of motion and critical damping. Critical damping, C critical. C critical obtained as either 2m b over a k over m or 2b over a multiplied by km. So this is the final answer for C critical we were supposed to find. So these are the final so we will go for next problem. Just let me know if you have any question. So one point I'd like to mention that for deriving equation of motion, if I have a stiffness K, as soon as I attach any mass like M, due to the weight of the mass, the system will be the mass will be displaced at and will be stationary at this point. So this length is a static deflection, right? And we usually consider the vibration started from a static equilibrium position, right? So if you plot free body diagram of the mass, you will have mg, right, and k static equilibrium at first case. So mg is always equal to k delta, right? So in order to derive equation of motion, you could ignore mg here, as mg will be cancelled out at the end by k delta star, and you will start writing equation of motion from this point, a static equilibrium position. Equilibrium position, and therefore the equation of motion would be mx double dot plus kx is equal to 0. Why? Because you just have a m displaced as a x after a static equilibrium position. And you have summation of forces applied at y, m, let's call it x here, right? So summation of momentum around in the direction of, so in the direction of x, mx double dot, which is equal to just minus kx double dot. It is not necessary to write minus k delta static plus mg, because they will be canceled out at the end of the day, right? This is unnecessary. So we only have mx double dot is equal to minus kx dot. Therefore, mx double dot plus kx is equal to 0. So if I want to summarize and give you a hint, if generally this statement is true, if amount of mass, if this amount of change if amount of mass can change the static equilibrium position, therefore we will not see mg in the equation of motion. Contrary, if like here, if like here we had, if I increase the mass, for example, from 5 kilogram to 10 kilogram, the static equilibrium position will be changed. This is just a quick note, quick hint, a trick. So just for double check, you are not supposed to see any mg here. If you see mg, you have to redo and check and do your calculation again. And if the static equilibrium position is not dependent on the mass, normally and generally, in most cases, we have to see mg in the equation of motion. For example, suppose we have a pendulum, right? If it is 5 kilogram or it is 500 kilogram, the static equilibrium position will not change, just here. For both cases, is here. So therefore, you have to see the mg in the equation of motion, LL. Theta double dot plus g over L theta is 0. Or could say m theta double dot plus mg L theta. So there should be mg in the problem. So just a quick hint, and in our problem specifically 2.42, as soon as you attach the system to the spring and damper, there should be a static equilibrium position, and here I just ignore, and I start my writing equation of motion, and I assume that this point you have to write. I assume that this is a static equilibrium position. You could, for the sake of simplicity, because they will be cancelled out if you start from this point, right? You could say, I assume this is the static equilibrium position. Why? Because the created momentum due to the mass in a static position will be cancelled out. I just assume this is a static equilibrium position, and I'll write my assumption and write my calculation from this point. This is the whole point I was trying to mention. And if you have any question, just ask me. For your reference, you could just derive equation of motion for this problem. For example, there is a spring, there is a rod, and if I want to give you a hint, so if I remember the question, we could derive equation of motion for this problem, K1, C1, and K2, C2 by using the Euler formula, A, B, for example, and J, just a typical example. You have to derive equation of motion. And if you have any question, you can ask me. And we will continue and we will solve 2.57 and 2.40 in the next session. If you have any question, just ask me and let me know. I will try to send this recorded session. I will try to upload the link in the Moodle or directly send you the link of the movie. Just let me know if you have any question. We are done for today, basically, and we will start the next problem, 2.57 and 2.40, and chapter 3 on basically Wednesday, next session. I will try to somehow zoom out for the next session to have a better view. So if you don't have any question, you could close the session and see you on Wednesday.